Hello friends, and welcome back to this course of electrochemistry. And now we will learn, last video we learned about Faraday's laws and how those things work, and in this video we will learn about the main concepts of electrochemistry and how to solve them, right? So let us start. So first of all, what you need to know about electrochemistry is the cell, right? So normally in electrochemistry we have two types of cell. One is the electrochemical cell. Electrochemical cell. What is the electrochemical cell? This electrochemical cell is a cell that where chemical energy is converted to electrical energy. Converted. So chemical energy is used to produce electrical energy. And then what is an electrolytic cell? An electrolytic cell is opposite, right? Where your electrical energy is converted to chemical energy. Great. So now we'll look into the aspects of how these things work. Okay, so let us first draw a diagram and understand it. So remember this LOA and lone. It means left oxidation, anode negative. Left oxidation, anode is negative. So anode is on the left where oxidation occurs and it is negative potential. Right. So let us draw it right. So let us draw our anode and let this be our cathode. Okay, so as I said, this has negative potential, so just give minus sign. This is a positive potential cathode, this is a positive sign. And the opposite of this is cathode. Like cathode is on the right, the reduction occurs and there is a positive potential, right? And suppose these are in two beakers which are filled with a solution, or you can say water as in. Okay, and we have a salt bridge connecting them. This is a salt bridge. Salt bridge, which is like KCl, you can KCl. Okay. And here you can see it is a your ZnSO4 solution, and here you can see it is a CuSO4 solution, right? So it is a place where oxidation is occurring. That means your so from this actually what reaction is happening is when oxidation is occurring, it means Zn2 plus 2 electron. Okay, so Zn is getting oxidized, and over here you also have your SO4 2 minus ions which go on to form the ZnSO4, and this is a copper electrode. So over here our copper is getting reduced. So Cu2 plus 2 electron is giving copper. And over here also you have SO4 2 minus, right? And these are connected via a battery. Right? And suppose electrons are flowing on this side, right? Electrons are flowing on this side. Great. So why is electron flowing on this side is because electrons are generated over here, right? And so electrons are going from this side to this side. That's why current is flowing on this side. The direction of current, the direction of electron flowing is opposite. Okay. And what is the role of salt bridge? So salt bridge is the bridge which actually connects the two cells, right? Your left hand side, right hand side, and therefore it completes the cell. It maintains the electrical neutrality of the cell. Electrical neutrality of the cell. So salt bridge can be KCl, KNO3, K2SO4, right? And or the solidified solution of electrolytes in agar-agar and gelatin, right? So that is our main concept, and right. So having understand this, we will go into some deeper concepts. So every element has a electrode potential, which is famously known as a reduction potential. Famously known as the reduction potential. So what is a reduction potential? It is the EMF value. Like EMF is given by E. EMF value that is generated when element is reduced. So suppose Li plus is reduced to Li. So what is the EMF value generated? Or the voltage that it is. And when it is standard conditions is in the temperature is 298 Kelvin, right? So in those conditions, it is given by E dot, right? So over here, our Li plus 2 Li, this EMF value is around E dot equals to minus 3.05. Okay, and our for hydrogen, let's say H plus 2 hydrogen. So like you can say plus electron, and we have 2 over here plus electron and half. Okay, great. So I don't need this. So for this E dot is 0 volt. And for fluorine, your F minus, sorry, your F2 to F minus plus electron F minus, this is E dot is equals to plus 2.87. So this is a negative, this is 0, this is positive. So what does it say? It says that as it goes down, as the reduction potential is more and more positive or higher in value, so this will get a higher chance to get reduced than the ones that are lower in value. So suppose just consider a scenario where I have lithium and thorium, both having in the same cell. So which one it is said will get oxidized and reduced. So because I know reduction potential of fluorine is more, so this will get reduced and this get oxidized. Okay, so this is the main concept. And over here, so fluorine gets reduced easily, right? Fluorine itself will get reduced, so it oxidizes other things. So it's a good oxidizing agent. Good, or you can say the strongest oxidizing agent. So lithium will itself get oxidized. It won't get reduced. So it's a good reducing agent. So over here you can see only that fluorine is a good oxidizing agent as it oxidizes lithium. Lithium is a good reducing agent as it reduces fluorine. So in that scenario. Okay. So and now what we have is our which is more reactive and which is not that much reactive. And for that we will use the reactivity of the metals. Okay, it actually depends on the tendency of substances to get oxidized. So if it gets oxidized easily, the reactivity is high. Right. That means our that means as we are going down the electrochemical series, the tendency of getting oxidized reduces, the tendency of getting reduced increases. So as the tendency of getting oxidized reduces, so as we go down, our reactivity decreases. Right. Okay. And now we will look into some main concepts of this electrochemistry. So the in a chemical reaction, the change in the free energy, right? The change in the free energy, that is del G, is given by the work done, electrical work done. That is actually equal to your charge into potential difference. And charge is given by, so del G, you can say charge is given by minus NF and potential difference is E. So this is an important formula. The del G for chemical reaction is given by minus NF. So for, if this is negative, it is spontaneous, right? It's negative, is spontaneous. For this to be negative, E has to be positive. This has to be positive. And E is normally given by E cathode, and E on the right hand side minus E on the left hand side, which is E anode. So if this is positive, we can say that the whole reaction is spontaneous. Right? Now we look into the famous Nernst potential. Okay, Nernst equation. So let us consider a scenario of taking zinc electrode. Great. So we can say that E of zinc is actually E dot minus RT by NF log of okay. So this our value of 2.303 RT by F is actually 0.059 at 298 K. So that is our Nernst equation, where you have the EMF value equals to the standard EMF value minus 2.303 RT by MF log of concentration of oxygen or concentration of reductant. And when it is an equilibrium condition, then the value of E is equal to 0, not E, not E dot, right? The value of E is 0, not E dot. Okay. Okay then. So now let us look into some numericals on this concept of Nernst equation. So the first question is this. I'll give you a tough question so that you can clear all your concepts through it. Okay. It's a good question. Question is, let me write the question using blue pen. Great. It says calculate EMF of cell at 298 Kelvin, which is the standard condition. And over here we have chromium 3 plus, which is 0.1 mole, and we have Fe 2 plus 0.01 molar. We have Fe, and it is given that E dot of Cr 3 plus Cr is equals to minus 0.75 volt, and E dot of Fe 2 plus slash F is minus 0.45 volts. Okay, so see, this is on the left hand side. Now I'm making this one green pen. This is on the left hand side. Left hand side means this is anode. It means over here oxidation is occurring. This is on the right hand side. It means this is cathode. It means over here reduction is occurring. Okay, so the equation that I want to form is this Cr. So over here oxidation is occurring. So Cr minus 3 electrons, we get Cr3 plus. Yeah, and over here we are getting reduction. So Fe2 plus 2 electron, we have F. We need to cancel out the electrons. So we multiply this by 2 and this by 3. So what we get over here is 2 Cr and 6 electrons gets cancelled out, plus 3 Fe2 plus, giving 2 Cr 3 plus 3 Fe. Okay, we are just interested in the concentration of our ions, not in the ones which are not in ionic form, right? Only concentration of the ions we will take. So the concentration of a normal element is taken as 1. So we are only interested in the ions. Okay, and okay, great. So we know that E is given by E cathode minus E anode. What is E cathode? Cathode is this one, right? So it will be minus 0.45 minus of minus 0.75 volt, which is equals to 0.3 volt. So we have E value, we have the concentration, we have N. N is what? 6. Because there are 6 electrons. So there are 6 electrons and 6 electrons over here which got cut. So now we can find out the EMF value from this. So the EMF value is E dot minus 0.059, because it is at 290 Kelvin, by N. N is what? 6. Log of this oxidant and log of reductant. And E dot is 0.3 volt minus 0.0591 by 6 log of what is the concentration of the oxidant. Concentration of the oxidant is your so which one was oxidant? This is oxidant 0.1 and this was 0.01. So this will be 0.1 by 0.01, and if you solve this, you get the answer. Okay. And one thing to note over here, that's why I said it's an interesting problem. See, I should actually write it explicitly. So this actually will be your E dot minus 0.0591 by 6 log of your. So oxidant is normally on the product side. So what is the product side? Cr3 plus. So Cr3 plus, and this will be on a like Fe2 plus, and Cr3 plus has 2 in front of it. Fe2 plus has 3 in front of it. So Cr3 plus to the power of 2 and Fe2 plus to the power of 3. So this will to the power of 2 and this will to the power of 3. Great. So this is our final equation, and if we solve this, so what is this actually? This is actually this part only I'm saying. This is log of your 10,000. Okay, which is actually equal to 4. Okay, so So our final answer is 0.3 minus 0.0591 by 6 into 4, which is equal to 0.261 volt. Great. So let us now do one more interesting problem. So we understood this how it's done. So we need to look for the stoichiometric as well, which goes to the power for this. Let us look into one more problem. For EK, it's a okay, I'll use my red pen. Calculate equilibrium constant for this Fe2 plus Ce4 plus using Fe3 plus, so Fe is getting oxidized and C should get reduced, which is happening. And so it's given that Fe3 plus Fe2 plus, the EMF for this E dot 0.68 volts, and the E dot for Ce4 plus Ce3 plus CMS 1.44 volt. So we need to find out the equilibrium constant, right? So for this, our E dot cell will be equals to, right, it's the cathode minus the anode. So which is cathode, which is anode, right? So over here, see what happens over here. Fe is getting, this is getting oxidized, this is getting reduced. The reduced one is our cathode. So this is our cathode. So cathode minus anode. So cathode is 1.44 minus 0.68. So our E cell will be for 0.76 volts. Okay, and equilibrium constant. So at equilibrium E is 0. Right. E dot is equals to 0.0591 by n log of the oxidant by reductant, which is actually given by K. Right. So do remember the fact that this 0.0591 value only comes from like RT 2.0303 by F, right? So two conditions, T has to be 298 Kelvin and this has to be in log form, because of log only this 2.303 is coming over here. If it's in ln, the 2.303 won't come, so it has to be log form. So N is what? Your N is around, see, we have to like cancel all the electrons, right? So this is getting, so it's one electron only because it's getting oxidized and reduced by one electron. So this is 0.0591 by 1 log K, and E dot is 0.76 volt. So you just find K from here and you get the answer. Okay, and K will be equal to 7.6 in part 2. So that's it, and practice this problem and you will be expert in advanced equation. Okay, all the best and have a great day ahead. God bless.